1 2s are 2, minus of minus 15 is plus 15, 2 plus 15 is 17, outside you have minus 17. If the determinant value will become 0, then it is a singular matrix. If the determinant value is not equal to 0, then it is a non-singular matrix. Any matrix cannot hold commutative property, that is AB cannot be equal to BA, and we have already proved it. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am lecturing in Vidyashram, the Temple of Excellence, Mysuru. In the last session, we have learned how to write the minus, cofactor and adjoint of a given matrix. So here in this session, we will extend the problems with the adjoint of matrix. We will be learning one more important concepts in the matrices and determinants, that is inverse of a square matrix. We know the adjoint exists only for a square matrix. Also, inverse also exists only for a square matrix. First, let us see the problems related to the adjoint of a matrix. First one, if A is equal to 1, minus 3, 2, 0, write the adjoint A. So, for a 2 cross 2 matrices, how we can find the adjoint of a matrix? That is, we interchange the principal diagonal element and we will change the sign of the other diagonal element. So, very simple to write. So, therefore, adjoint of A is interchange the principal diagonal element, change the sign in the other diagonal. So, we have minus 3, we will write plus 3 and here it is minus 2. So, this is the adjoint of a 2 cross 2 matrix given. Next, if A is equal to 1, 3, 4, 5, prove that A into adjoint A into A is equal to determinant A into I. So, we have already learned the concept through the theorem. Now, let's prove this statement. So, we have A, let's write adjoint A. So, adjoint A is equal to interchange the principal diagonal element 5, 1, change the sign minus 3, minus 4. Now, first let's see what is A into adjoint A. A into adjoint A, that is the product of 1, 3, 4, 5 into 5 minus 3 minus 4, 1. So, this is equal to, so we know how to product two matrices, first row into first column, second row into first column. Similarly, first row into second column, second row into second column. So, now let's see first row into first column. 1 5 is a 5 plus 3 into minus 4 minus 12. Next, first row into second column. Minus 1 into 3 minus 3. 3 into 1, 3. Next, we will go for second row, first column. 4 5s are 20. 4 5s are minus 20. Next, 4 3s are minus 12. Next, 5 1s are 5. So, if you solve this, you will get A into adjoint A as, so minus 7, 0, 0, minus 7. So, this is now A into adjoint A. Let's see adjoint A into A. Now, adjoint A into A. So, what is our adjoint A? 5, minus 3, minus 4, 1. What is A? 1, 3, 4, 5. Let's see the product. 5 1s are 5 and it is minus 12. Next, 5 3s are 15. Minus 3 into 5 minus 15. Minus 4 into 1 minus 4. 4 1s are 4. Minus 4 minus 12 plus 5. So, if you solve this again, adjoint A into A is equal to minus 7, 0, 0, minus 7. Now, let's see the last one, determinant A into I. So, determinant A into I. So, let's calculate the determinant of 1, 3, 4, 5. Into I means we have to take here, since we have already taken here a square matrix of order 2 cross 2, I also must be a square matrix of order 2 cross 2. Let's find the value of the determinant. 1 5s are 5, 4 3s are minus 12 into 1 0 0 1. So, here on solving this, you will get the value as minus 7. So, therefore, determinant A into I is minus 7 into 1 minus 7, 0, 0, minus 7. So look at these equations we have. Take this as equation 1, take this as equation 2, take this as equation 3. From 1, 2 and 3, you can observe the resultant matrix is the same. So therefore what I can write, A into adjoint A is equal to adjoint A into A is equal to determinant A into I. Hence proved. Okay, so previously we have done the same problem for a 2 cross 2 matrix. Now let's do it for a 3 cross 3 matrix. But before finding the adjoint, we need to find the cofactors. So first let us write the cofactors of matrix A. That is, we will write the determinant of each values. So we can write it in the form of, so for 1 it is, so plus, write the remaining 0, 2, minus 1, 1. Next, minus determinant of, leave the row, leave the column containing 2, we have 5, 2, 1, 1. 5, 2, 1, 1. Next, plus, leave the row and column 5, 0, 1, minus 1. 5, 0, 1, minus 1. Next, we have minus. We will go for the second row elements. Write the cofactors of 5. So 5 is 2 minus 3 minus 1, 1. 2 minus 3 minus 1, 1. Next, we have plus 1 minus 3, 1, 1. 1 minus 3, 1, 1. Next, minus. So minus, leaving minus, 1, 2, 1, minus 1. 1, 2, 1, minus 1. Next, we have 1. So it is plus. So for plus, it is 2 minus 3, 0, 2. 2 minus 3, 0, 2. Next, we have minus. So leave the column and row. 1 minus 3, 5, 2. 1 minus 3, 5, 2. Next, plus. For the last element, the minor is 1, 2, 5, 0. 1, 2, 5, 0. So like this also you can do in a matrix also. So this is a matrix. Let us write in a square brackets. So this is a cofactor matrix of the elements in A. So taking the transpose of the cofactor matrix will give you the adjoint of a matrix. So now let's see the values here we have. So what are the elements we get? So 0 ones are 0, minus of minus 2 is plus 2. So outside also it is 2, so we will write 2. Next, 5 ones are 5, minus 2, 3, outside minus, so we will write it as minus 3. Next, minus 5 minus 0, so it is minus 5. Next, 2 minus 3 minus 1, outside it becomes plus 1. Next, 1 plus 3 is 4, outside is also plus, so it is 4. Next, minus 1 minus 2 is minus 3, outside minus, it becomes plus 3. So next is 2 2s are 4 minus 0, which becomes 4. Next is 1 2s are 2, minus of minus 15 is plus 15, 2 plus 15 is 17, outside you have minus 17. 0 minus 10, which becomes minus 10. So this is the cofactor matrix you got. Now let's write the adjoint of the matrix. Adjoint of a matrix is nothing but the transposition of this matrix, that is writing columns into rows. So what we will get? 2, 1, 4, minus 3, 4, minus 17, minus 5, 3, minus 10. So this is our adjoint matrix. Now let us prove this. A into adjoint A is equal to adjoint A into A is equal to determinant A into I. Let us first find out A into adjoint A. So A into adjoint A matrix. So A we have 1, 2, minus 3. Next 5, 0, 2. Next 1, minus 1, 1. Next adjoint A 2, 1, 4. Minus 3, 4, minus 17, minus 5, 3, minus 10. So now the same operation for the multiplication, first row, first column, first row, second column, first row, third column. So let us write the given matrix now. 1 2s are 2, 2 minus 3 minus 6, minus 3 into minus 5 plus 15. So first row, first column finished. Next we will do first row, second column. 1 1s are 1, 2 4s are 8, 3 minus 3 becomes minus 9. Next, first row, last column, 1 4s are 4, 2 into minus 17 becomes minus 34. Next, minus 3 into minus 10 plus 30. So this is done. Now we will move for second row, first column. 5 2s are 10. Next it is 0. Next, minus 10. Next, 5 1s are 5, 0, 6. Next, 5 4s are 20. Next 0. Next 2 into minus 10 minus 20. Next 1 2s are 2. Last row first column. Last row second column. Last row third column. So 2. Next we have minus 1 into minus 3 plus 3. 1 into minus 5 minus 5. Next we have 1 into 1 which is 1 minus 4. Next plus 3. 1 4s are 4, minus 1 into minus 17 plus 17, next minus 10. So this is the factors we got here. So after solving this, adding 2 minus 6 is minus 4, minus 5 plus 15 is 11. So here it becomes 0, 34 minus 34 0, 10 minus 10 0, 5 plus 6 11, 20 minus 20 0, 5 minus 5 0, 4 minus 4 is 0. Next you have 21 minus 10, that is 11. So therefore you will get A into adjoint A as 11, 0, 0, 0, 11, 0, 0, 0, 11. So this is what A into adjoint A. Now in the similar way, you can multiply adjoint A into A. So after multiplying adjoint A into A, you will have the same process of multiplication again. Let's write what is adjoint A. That is 2, 1, 4. Next, minus 3, 4, minus 17. Next, minus 5, 3, minus 10. Minus 5, 3, minus 10. Now let's take up A. 1, 2, minus 3, 5, 0, 2. 5, 0, 2, 1, minus 1, 1. So this is our A. Now let us multiply. Again, first row, first column, 2 1s are 2, 5 1s are 5, 4 1s are 4. 2 2s are 4, 1 0s are 0, minus 4. 2 minus 6 plus 2 plus 4. Next, minus 3, 20, minus 17. Next we have minus 6, 0, plus 17. Minus 3, 9 we have. 4 2s are 8, minus 17. Next, minus 5, 15, minus 10. Next, minus 10, 0, plus 10. Next again we have 15, 6. Next, minus 10. So adding all this. So let's add this. What we will get? See, that is adjoint A into A. So here first one is 11. 4 minus 4 becomes 0. So next we have minus 6 plus 2 plus 4 which becomes 0. 0, 11, 0. Next again minus 15 plus 15 cancels. Minus 10 plus 10 cancel. 21 minus 10 again it becomes 0, 0, 11. So let me take this as equation 2. Let me take this as equation 1. The last one we need to find out is determinant A into I. First let us see what is determinant A. So first write determinant of A. What is A we have? 1, 2 minus 3. Next 5, 0, 2, 1 minus 1, 1. So let's find. So we will take the first row element 1 into cofactors of this 0 plus 2. Next minus 2 For this it is minus because plus minus plus operation here. So this is minus. So minus 2. Leave the row and column 5 minus 2. The last one is plus minus 3 we have. So leave the column and row minus 5 minus 0. So on solving this we have 2. Next we have minus 6. Next we have plus 15. So 15 plus 2, 17 minus 6, we get 11. So the determinant A value is 11. Now let's take determinant A into I. That is 11 into 1, 0, 0, 0, 1, 0, 0, 0, 1. So on multiplying the 11 inside the matrix, 11, 0, 0, 0, 11, 0, 0, 0, 11. So take this as equation 3. Now observe A into adjoint A into A, and determinant A into I. All are the unit matrix along with 11 as a factor. So therefore what I can conclude, A into adjoint A is equal to adjoint A into A is equal to determinant A into I. Hence proved. Next, verify adjoint of AB is equal to adjoint B adjoint A if the matrix A is 2, minus 3, 1, minus 6 and matrix B is minus 1, 4, 1 into minus 2. So let's find out AB first. AB is the product of these two matrices. 2 into minus 1 minus 2, minus 3 into 1 minus 3. Next, 2 4s are 8, 3 2s are 6. 1 into minus 1 minus 1, minus 6 into 1 minus 6. 1 into 4 4, 6 2s are 12. So now see what is AB. Matrix AB is minus 5, 14. Next here it is minus 7. Next here it is 16. So this is determinant AB. Now let's take adjoint AB. Adjoint of AB. So when writing adjoint of 2 cross 2 matrix, interchange the elements of principal diagonal 16 and minus 5. Change the sign here. It is minus 14 and this is 7. So let me take this as equation 1. Now let's write adjoint of A. Adjoint A. Adjoint A is minus 6, 3, minus 1, 2. Adjoint B. Adjoint B is minus 2, minus 1, minus 4, minus 1. Now let us see adjoint B into adjoint A. So therefore, let's write adjoint B into adjoint A. So what is adjoint B? We have minus 2, minus 4, minus 1, minus 1. Adjoint A is minus 6, 3, minus 1, 2. Let's take the product of this. So minus 2, minus 6, 12 plus 4. Next, minus 2 we have minus 6 and here it is minus 8. Next, 6 plus 1. Next, minus 3, minus 2. So let's see it. We have 16, minus 14, 7, minus 5. So this is adjoint B into adjoint A. So take this as equation 2. Observe both equation 1 and equation 2, you have the same matrix. So therefore what I can conclude, adjoint of AB can be written as adjoint B into adjoint A. So hence proved. Next question, if 5x2 minus 10, 1 is a singular matrix, find x. We have learned what is singular and non-singular. If the determinant value will become 0, then it is a singular matrix. If the determinant value is not equal to 0, then it is a non-singular matrix. Clearly they have given it's a singular matrix. So that means the determinant of the given matrix will be equal to 0 because given it's a singular matrix. Now write 5x into 1, 5x. Minus 10 into 2 is minus 20. Minus of minus 20 is plus 20. So therefore here we get 5x is equal to minus 20. X is equal to minus 4. So this is the value of the x. So next we will move on to the important concept called the inverse of a square matrix. What is this inverse of a square matrix? If A and B are two square matrices of the same order, then if AB is equal to BA is equal to I, if you take the product of AB and BA so that it results in an unit matrix, then we call matrix B is inverse of A. So in other words, what we can say, any matrix cannot hold commutative property. That is, AB cannot be equal to BA, and we have already proved it. But whenever you have AB is equal to BA, that means one matrix is inverse of the other. They are satisfying the condition AB is equal to BA is equal to I. That is, their product will result in an unit matrix. Hence, we call B is a inverse of matrix A. And we have a formula to find out inverse of any matrix A. That is, A inverse is equal to adjoint A divided by determinant A. So this A inverse can be taken as B, another matrix B. Hence we call B. And when you multiply A and A inverse, it always results with the unit matrix. So therefore, A inverse can be obtained by adjoint A divided by determinant A, where the determinant A must be non-singular matrix. It cannot be singular matrix. So few points to be noted here. If A inverse exists, means the determinant A is not equal to 0. That means A must be a non-singular. Hence we call A inverse is unique. Suppose I said A into A inverse into A is equal to I. It is possible if A inverse is non-singular, then so it is such that A is non-singular, then we call A inverse is also non-singular matrix, because when it becomes singular matrix, the denominator becomes 0. Hence, the determinant value should not be equal to 0. Then only we say A inverse exists. Next, again, when you apply the determinant value for A and A inverse, since it is equal to I, the determinant of a unit matrix is always equal to 1. Hence, we can write determinant of A inverse is the reciprocal of the determinant. If A is any square matrix and its value is determinant A, then the determinant of A inverse is 1 over determinant A. They are reciprocal to each other. The value of the determinants are reciprocal to each other. Next, if A and B are square matrices of same order, AB whole inverse, that is the product of the matrix and its inverse, can be written in the form of B inverse into A inverse. As we have proved earlier, that is adjoint of AB is adjoint B into adjoint A. Similarly, AB whole inverse can be equal to B inverse into A inverse. So first question is, find A inverse. We know that A inverse is equal to adjoint A divided by determinant A. So let's find adjoint A. What is adjoint A? Interchange the principal diagonal elements 2, 2 and change the sign, -1, -1. Find out the determinant value of A. 2 2s are 4, -1, which is equal to 3. This must not be equal to 0. So therefore, A inverse is equal to adjoint A is 2, -1, 2 divided by 3. So this implies A inverse is equal to 2 by 3, -1 by 3, -1 by 3, 2 by 3. So this is the new matrix, which is the inverse of a given matrix. So next one, if A is equal to 3 minus 1, 1, 2, show that A square minus 5A plus 7I is equal to 0, and hence find A inverse. So by verifying the given equation, we are supposed to calculate A inverse. Let's verify A square. So let's see what is A square. So that is 3, 1, minus 1, 2, 3, 1, minus 1, 2, minus 5 into A, 3, 1, minus 1, 2, plus 7 into I, 1, 0, 0, 1. Let's verify this. 3 3s are 9, minus 1. So which is 8. 3 1s are 3, 2 1s are 2. You will get 5. So minus 3 minus 2 minus 5. Next minus 1 plus 4. So you have 3. So this is the product of the matrix A square. Now let us multiply this. 5 3s are, you will get 15. 5 1s are 5. Next you have minus 5. Next 5 2s are 10. Next you have 7 0 0 7. Let's see the result. 8 plus 7 15 minus 15 0. 5 minus 5 plus 0 0. Minus 5 minus of minus 5 plus 5 plus 0 0. Next 3 minus 10 minus 7 minus 7 plus 7 0. So therefore we have A square minus 5A plus 7I is equal to null matrix. Now to find A inverse here, let us multiply A inverse on both sides. So if you multiply A inverse, this is A inverse into A square can be written as A into A. Here minus 5 A inverse into A plus 7 A inverse into I, A inverse into null matrix. So multiply anything with the null matrix, the result will become 0. So here previously A inverse into A, the commutative law holds and the value will be equal to the identity matrix. So this is I into A minus 5 into I plus 7 into A inverse is equal to 0. Next we have I into A is nothing but A, 5I plus 7A inverse is equal to 0. Or if you want 7A inverse, it is 5I minus A. So first let us calculate 5I minus A. So 5, 0. 5I is nothing but 5005. And A is here 3, 1, minus 1, 2. So 7 into A inverse. So A inverse into 7. 5 minus 3 is 2. And here minus 1. Minus of minus 1 plus 1. 5 minus 2 is 3. So therefore, A inverse is equal to, we have the matrix 2 minus 1, 1, 3. So divide the matrix by 7. So therefore, A inverse is equal to 2 by 7, minus 1 by 7, 1 by 7, 3 by 7. So this is the inverse of a given matrix. So this is also one of the important question for your examination. That is, we need to solve and show that the equation will result in a null matrix. Then to find out A inverse, we have to multiply A inverse on both sides. By using the properties of the inverse of a matrix, we will get A inverse. So next question, find the inverse of a matrix 2, minus 1, 3, 2. So first let us find out adjoint of a matrix because a formula should have adjoint and determinant. So again 2, 2, 1, minus 3. Let's find out determinant A. It is 2 2s are 4 minus of minus 3 which is equal to 7. So therefore A inverse is equal to adjoint A divided by determinant A. So therefore I can write A inverse is equal to each element divided by 7. So that is 2 by 7, 1 by 7, minus 3 by 7, 2 by 7. So this is the inverse of a matrix. Next, if A is equal to 2, 3, 1, minus 1, B is equal to 1, minus 2, minus 1, 3, verify that AB whole inverse is equal to B inverse into A inverse. So first let us find out A into B. A into B is 2 1s are 2, minus 3. 2 into minus 2, minus 4. 3 3s are 9. 1 1s are 1, plus 4. 1 into minus 2, minus 2. Minus 4 3s are minus 12. So the value is equal to minus 1, 5. Next we have 5 here, minus 14. So let's calculate determinant AB. Determinant AB is, so minus 14, 14, minus 25, which is equal to minus 11. Let's calculate adjoint of AB. Adjoint of AB is minus 14, minus 5, minus 5 and minus 1. So therefore, AB whole inverse will be equal to adjoint AB by determinant AB. So therefore, here I can write it as minus 1 by 11. Outside I'll keep it. It is minus 14, minus 5, minus 5, minus 1. Because A inverse or any inverse of a matrix is always adjoint A divided by determinant A. Using this formula, so since determinant A is minus 11, I am writing it in the form of minus 1 by 11 and I am keeping it outside. Let me take this as equation 1. Now let's find out B inverse, A inverse. So first find determinant A. Determinant A is minus 8, minus 3, which is equal to minus 11. Find adjoint A. Adjoint A is minus 4, minus 3, minus 1, 2. So A inverse can be written as minus 1 by 11, minus 4, minus 3, minus 1, 2. Now let's find out determinant of B. Determinant of B is 3 into minus 2, which is equal to 1. Now find out adjoint of B. So adjoint B is 3, 2, 1, 1. So now let's find out B inverse. So B inverse is equal to 3, 2, 1, 1 by 1, which becomes 3, 2, 1, 1 only. Now let's find B inverse into A inverse. So B inverse is 3, 2, 1, 1. A inverse is minus 1 by 11 into matrix is minus 4, minus 3, minus 1, 2. So let's keep minus 1 by 11 outside. Let's multiply the matrices. 3, minus 12, minus 2. Next, minus 9, plus 4. Next, minus 4, minus 1. Next, we have minus 3, plus 2. So we have minus 1 by 11, minus 14, minus 5, 5, minus 5, minus 1. So this is B inverse, A inverse. Let's take it as equation 2 and this is our equation 1. We have minus 1 by 11, minus 14, minus 5, minus 5, minus 1. Minus 1 by 11, minus 14, minus 5, minus 5, minus 1. So therefore what I can conclude, inverse of AB is equal to inverse of B dot inverse of A, or AB whole inverse is equal to B inverse into A inverse. Hence proved. So the concept of adjoint and inverse may arises for 3 marks or 5 marks question whenever you are going to find out the inverse through matrix method also, which we will discuss in the next session. Meet you in the next session. Until then, keep watching, keep learning, keep exploring. Thank you.